It's time for Math with Mr. Young. Lesson 113, Volume of Pyramids, Cones, and Spheres. Let's begin with a power-up. You can use the worksheet provided, or simply pause the video and use a blank sheet of notebook paper to answer the problems on your screen. Go ahead and pause now, and resume once you've completed all of the problems in this power-up. In this power-up, we get to review adding, subtracting, multiplying, and dividing numbers and variables. First, we have 6x plus 2x. To solve expressions like these with variables, the way I try to make sense of it is to put something concrete in place of the variable at first. So instead of saying x, I'd give it some concrete value. Let's imagine that x is an inch. If we had 6 inches plus 2 inches, that would be easy, correct? It would just be 8 inches. So 6x's plus 2x's is also easy. It's just 8x's, or 8x. And there's your answer. This next problem is just as easy as before. 6x minus 2x. Let's imagine something concrete for this variable. This time, maybe x is a foot. 6 feet minus 2 feet would be easy, right? It's just 4 feet. So 6x minus 2x is 4x. And that's the answer. Our next problem has 6x times 2x. For this kind of problem, it also helps to think concretely first. Let's imagine that x means centimeter this time. So I start with 6 centimeters. If I were to double my 6 centimeters, I would have 12 centimeters. So 6 centimeters times 2 would be 12 centimeters. That means that 6x times 2 would be 12x. But that's not what the problem says, is it? In the problem, we're not just multiplying by 2, which would mean doubling, we're multiplying by 2x. So we can't just think of 6 centimeters multiplied by 2, we need to think of 6 centimeters multiplied by 2 centimeters. Can you think of anything that is measured 6 centimeters by 2 centimeters? How about a rectangle that is 6 centimeters long and 2 centimeters wide? To find the area of this rectangle, you'd multiply the 6 centimeters by the 2 centimeters. And what's the result? Our result is 12 centimeters squared. 6 centimeters times 2 centimeters is 12 centimeters squared. So our 6x times 2x must be 12x squared. There's our answer. The next problem features division. 6x divided by 2x. To solve this one, I want you to remember that whenever you have something in the numerator and the denominator, they cancel out. Here we see x in the numerator and in the denominator, so we can simply cancel those two x's. That leaves us with 6 over 2. You can solve 6 over 2, can't you? 6 divided by 2 is 3. Our answer is 3. Our next problems will be similar to these first 4, but they will now have more variables. This won't change how we solve them. Up first, we have 9xy plus 3xy. Remember that adding 9 something plus 3 of that same something just gives us 12 something. So 9xy plus 3xy will give us 12 xy. Pretty easy, right? Our next problem trades addition for subtraction. 9xy minus 3xy. Again, 9 of something minus 3 of something would simply be 6 of that something. So 9xy minus 3xy will simply be 6xy. That's the answer. Now we have multiplication again. 9xy times 3xy. This time, I'm going to show you a shortcut on how to solve this. You can think of 9xy as being 9 times x times y. So write it that way. You can also think of 3xy as being 3 times x times y. Write it out that way as well. Now, using the commutative property of multiplication, which is just a fancy way of saying that you can move the numbers and variables around, let's group the constants together and the different variables together. 9 times x times y times 3 times x times y becomes 9 times 3 times x times y times y. Remember, any number multiplied by itself is that number squared. So x times x here is x squared. The same thing goes for this y times y. That is y squared. So now all we have left is 9 times 3, which is 27. So our answer is 27 x squared y squared. Nice job. Now we have division again. 9xy over 3xy. Just like our last division problem, let's cancel. X on top cancels with x on bottom. Y on top cancels with y on bottom. That leaves us with 9 over 3. 9 divided by 3 is 3. That's our answer. Next up, we have x plus y plus x. To figure out how we're supposed to solve, let's imagine something concrete for our variables again. Let's imagine that this x is a foot and this y is an inch. If this problem was a foot plus an inch plus another foot, it would be pretty easy to find the answer. The answer would be 2 feet and 1 inch. Something to notice here is that simply saying a foot or an inch is the same thing as saying 1 foot or 1 inch. A foot plus an inch plus a foot is the same thing as saying 1 foot plus 1 inch plus 1 foot, which is why our answer is 2 feet and 1 inch. Let's apply this to our problem. X plus y plus x is the same as 1x plus 1y plus 1x. 1x and 1x can combine, just like 1 foot and 1 foot combined. It becomes 2x. So our answer is 2x plus 1y, or simply 2x plus y. Our next problem is similar, but has subtraction in it. X plus y minus x. Once again, let's imagine this problem with feet and inches. A foot plus an inch minus a foot would be what? Well, let's put in our implied ones. This problem wouldn't change if we said 1 foot plus 1 inch minus 1 foot. What's 1 foot minus 1 foot? 0 feet. So our answer would be 0 feet plus 1 inch. You don't have to say the 0 feet part, so we can erase that. Our answer is simply an inch. Now, let's go back to our problem. First, add in the implied ones. 1x plus 1y minus 1x. Subtract this 1x from this 1x. 1 minus 1 is 0. So our answer is 0x plus 1y. We can simplify this to 1y, or just y. Now, on to multiplication again. X times y times negative x. Remember a previous lesson where we learned about multiplying negatives. When multiplying a bunch of numbers or variables together that include negatives, first do the multiplying and worry about figuring out whether the product is positive or negative at the end. Here we have x times y times x. X times x can become x squared. So our product is x squared times y, or x squared y. Now, should our answer be positive or negative? Well, if the number of negatives being multiplied together is odd, then our answer must be negative. And we have one negative, which is an odd number. So this answer will be negative x squared y. Now, on to division. X times y over x. Hopefully you remember that, to solve this kind of problem, we can cancel. The x on top and the x on bottom cancel each other out. We're left with just the one y on top. So our answer is y. Way to go! Now the problems get a little bit trickier. Up first, we have 3x plus 3. To solve this one, I want you to think about what you learned in a previous lesson about like terms. Do you see any like terms here? Remember, like terms are terms with the same variable part. The variable part of 3x is x. The variable part of this x, which is also 1x, is x also. So these are like terms, and we can combine them. 3 of something plus 1 of that same something is 4 somethings, so 3x and 1x combine to become 4x. We can't do anything to simplify this 3, so we just leave it as is. Our final answer is 4x plus 3. This next problem with subtraction works the same way. 3x minus x minus 3. Once again, find the like terms. 3x and x are the like terms, just like in our previous problem. This time, the problem is asking us to subtract 1x from 3x. 3 minus 1 is 2, so 3x minus 1x is 2x. Once again, we leave this constant as is, and so our final answer is 2x minus 3. Now multiplication. 3x times negative x times negative 3. We're multiplying negatives again, so do the multiplication part first, and we'll worry about whether the answer is positive or negative at the end. Something to remember here is that when we're multiplying, you might want to write out 3x as 3 times x. So, disregarding the negatives for now, we have 3 times x times 3. Hopefully you remember that this x times x can become x squared. Now we multiply this 3 times 3 to get 9. So far, we have 9x squared. Let's see if our answer is supposed to be positive or negative. Back here in the problem, we had a negative here and a negative here. That's 2 negatives, which is an even number. That means our answer is going to be positive. So our answer is positive 9x squared. Finally, we have 2x times 8xy over 4y. For this problem, which has multiplication and division, it will help you to write out 2x, 8xy, and 4y in this way. 2x becomes 2 times x. 8xy becomes 8 times x times y. And 4y becomes 4 times y. Now, let's use the commutative property to do a little rearranging. Let's group the constants together up top. Let's also bring the x's next to each other. So now our problem reads 2 times 8 times x times y over 4 times y. Let's first multiply this 2 and 8 together to simplify that part. 2 times 8 is 16. Now, notice that there is a y on top and a y on bottom. Those y's cancel out. Also, we can pull a 4 out of the top and the bottom. 16 divided by 4 is 4, and the 4 on the bottom divided by 4 is 1. So 16 over 4 simplified to 4 over 1. Now we have 4 times x on top, and 1 on the bottom. We don't need the denominator anymore, because anything divided by 1 is just itself. So now we have 4 times x times x. X times x becomes x squared. That leaves 4x squared. That's it, we did it. Okay, pull out your notes page. Today we're going to memorize formulas for finding the volume of a few different geometric solids: pyramids, cones, and spheres. Hopefully, after demonstrating how these formulas work the way they do, you'll remember them without even needing to memorize anything. So let's start with the pyramid first. Take a look at this cube. Look inside of it. You should see some pyramids in there. Now consider the bottom yellow pyramid. Notice that the base of that pyramid is also the bottom face of the cube. Also notice how the pyramid is half as tall as the cube, because its peak is in the center. Can you tell how many pyramids are inside this cube here? If you guessed that there is one pyramid for each face of the cube, you're right. And that means since there are 6 faces on a cube, 4 around the sides plus 1 on top and bottom, then there must be 6 pyramids in there. Let's see if we're right. Looky there! We have 6 equal pyramids that are exactly half as tall as our original cube. Those 6 pyramids can come back together to make the original cube. So, if a pyramid that is 1/2 as tall as the cube makes up 1/6 of the cube's volume, what fraction of the volume of the cube would be represented by a pyramid that is twice that tall, going all the way from the base of the cube to the top? If you guessed that this pyramid will have twice the volume of one that is half as tall, you are correct. And if that is true, that means that this pyramid should make up 1/3 of the volume of the entire cube. Let's look at it another way. Do you remember the formula for the area of a triangle? It was 1/2 times the base times the height. That means if the base stays the same and the height stays the same, then the area of the triangle should also be the same. Notice how as I'm changing the shape of this triangle, the base and height are staying the same. So that means that the area of the triangle is also staying the same. It's easy to see if we stop here that the area of this triangle is exactly half the area of a square with the same height and base. So in 2 dimensions, if we start with a square, which has an area of base times height, and we pinch the top of it to a single point, we can see that we've reduced the area by half, giving us our formula, base times height times 1/2. And no matter where we put the top of our triangle, so long as we're not changing the height, its area will remain 1/2 the area of the square. That was 2 dimensions, and the resulting formula was 1/2 base times height. Now consider a solid object with 3 dimensions. If we start with a cube and pinch the top of it to a single point, how does this affect our volume? It will help to visualize it. First, remember that changing the location of the top of our pyramid, so long as we're not changing the height, won't change the volume. So, just like we did with our triangle, let's move the top of the pyramid to the corner and see if this will help us visualize how its volume relates to the volume of the cube. At first glance, maybe it's not quite so obvious that this pyramid's volume is exactly 1/3 of the volume of the cube. But watch this next part carefully, and you'll see that it is. Watch as I pull a pyramid with that exact same shape out of this cube. I'm pausing here so you can double-check that this pyramid we just removed has a base that is the same as our original cube, and also a height that matches the original cube. Now, let's cut what's left of the cube in half, right down the middle. It looks like it's already divided for us into a yellow half and a purple half. But if we separate these 2 halves, what do you think they will look like? Take a second to look for yourself and see if you can visualize the shape of all 3 sections. Now I'll break them apart for you to see it. Voila! 3 exactly equal sections of the cube. Putting 3 three-dimensional pyramids with the same base and height together will equal the volume of a 3-dimensional cube with that same base and height. Just like how putting 2 two-dimensional triangles together produced the area of a square. So, if the formula for the 2-dimensional triangle is 1/2 base times height, what do you think the formula for our pyramid will be? It will be 1/3 base times height. Let's go ahead and write that down in our notes. The formula for the volume of a pyramid is 1/3 times the area of the base times the height. Let's take a look one more time in a slightly different way, so we never forget that 3 is the number of pyramids a cube divides into. Considering the same 3 pyramids from before, look at how many faces of the cube belong to each pyramid. Considering the pink pyramid first, we see that the bottom face of the cube is entirely pink. So that's 1 whole face. This face closest to us is half pink, so that's 1/2. And this other face on the side is also half pink, so that's a total of 2 faces of the cube that are pink. Do you remember how many faces a cube has total? 6. So each of these pyramids makes up 2 of the 6 faces of the cube. These smaller pyramids got 1 face of the cube to themselves and were 1/6 of the total volume. These larger pyramids get 2 faces of the cube to themselves and make up 2/6 or 1/3 of its volume. Okay, hopefully now you'll never forget that a pyramid inscribed in a cube comprises 1/3 of that cube. And that can help you remember the pyramid formula 1/3 base times height. But this formula will remain true for other kinds of pyramids too. which can be made from bases that are different polygons. No matter how many sides the polygon at the base of our pyramid has, the volume of the pyramid will be 1/3 of the volume of whatever right solid has that same base. Remember, the right solid's volume is area of the base times height. So the pyramid's volume will always be 1/3 of the area of the base times the height. As I'm increasing the number of sides in our pyramid, do you see what the base is becoming more and more like? It's approaching a circle. If we make a circle our base, we have a cone. And the cone has the same relationship to its right solid, the cylinder, that our pyramids had with theirs. So a cone's volume is also 1/3 times the area of the base times the height. So let's add that to our notes too. This first formula is not just for pyramids, but also for cones. Okay, there's one last thing I need to show you. Think of a cylinder with a diameter of 1 unit and a height of 1 unit. Now, inside this cylinder, let's inscribe 2 cones. If we inscribed 1 cone, we now know that it would have a volume of 1/3 of the cylinder. But if we look at this figure more closely, we'll notice that the bottom cone is 1/3 of the bottom half, while the top cone is 1/3 of the top half. So both cones together should be 1/3 of both halves of the cylinder together. Now, I want you to imagine poking a straw through the cylinder so that you can blow air inside both cones. If you were to blow into the cones until you doubled the amount of air inside them, you would end up with a sphere. The cones were 1/3 of the volume of the cylinder, and now you've doubled that. So, what do you think is the volume of the inscribed sphere, then? It's 2/3 of the volume of our unit cylinder. So let's go back to our notes and find the formula for the volume of a sphere. It should be the area of the base, pi r squared, times the height, which is 2 radii long in this case, so 2r, times 2/3. Let's simplify that. The easiest way is to write it all out as multiplication. The area of the base is pi times r. We multiply that by 2 times r, and then we multiply that by 2/3. We've got 3 r's here, so let's combine those to get r cubed. We've also got a 2 and a 2/3, so let's combine those to get 4/3. And then we have pi. So all together we have 4/3 pi r cubed. That's it. That's the formula for the volume of a sphere, and we derived it simply from the knowledge that it is twice the volume of a cone. Pretty cool. Okay, now let's do an example problem. A cylinder has a radius of 3 inches and a height of 6 inches. What is the volume of the cylinder, and an inscribed cone, and an inscribed sphere? Use 3.14 as an estimate for pi. Let's start by finding the volume of the cylinder. To do that, we use the formula we learned in Lesson 95. The volume of any right solid, and a cylinder is a right solid, is found by taking the area of the base and multiplying by the height. So let's do that. The base is a circle, so we'll need to remember our formula for the area of a circle, which is pi r squared. In this case, r is 3 inches. So the area of the base will be 3 squared times pi. Multiplying that out gets us 28.26 square inches. Now we need to multiply that by the height, which is 6 inches. That gets us 169.56 cubic inches. Now let's find the cone. The formula for the cone is 1/3 times the area of the base times the height. So we could plug all our numbers in again, or we could notice that we've already done most of the work already. Area of the base times the height is right here, the volume of the cylinder. So all we have left to do is find 1/3 of that. 1/3 times 169.56 is 56.52. So our cone has a volume of 56.52 cubic inches. Now the sphere. The formula for a sphere is 4/3 pi r cubed. So let's plug in our numbers. R is 3 inches. So r cubed is 27 cubic inches. Multiply that by pi. That gives us 84.78 cubic inches. Now we must multiply by 4/3. That gives us 113.04. So the volume of our sphere is 113.04 cubic inches. Some of you are probably like, hey, wait a minute, there's a much easier way to find that answer. And you're right. We could have simply multiplied the volume of the cone times 2. So let's go ahead and do that to check our work. Yep, it looks like we found the right answer. Well done. Now it's time to open your textbook. To complete this lesson, start by doing the example problems provided. Try to solve them on your own before you look at the solution and the steps. Once you think you have the correct answer, check your work by walking through the steps, making sure that you arrived at the solution the correct way. Once you are done, you're ready to move on to your homework. See you next time!